Okay, so now we're going to introduce corollary 3. And in corollary 3 it says, in a vector space, any finite set of... let me say that again. In any vector space, any finite set has a linearly independent subset with the same span. Okay, so we're going to do this proof. Now in the proof, we're going to just take a set S, right? So let's take a set S, which equals a set of vectors from the vector space, right? Okay, now, keep in mind, now I'm not going to write this down, but if S is linearly independent, then we're done. Okay, we'd be done, right? There'd be nothing to prove, right? So let's assume that S is dependent. Okay, so now, if S is dependent, then we know that by definition, it contains a vector V that is a linear combination of the others. Okay. Right? So by definition, there is a vector V1 that is a linear combination of the others. Okay, so now we're going to define another set. Okay, so now let's define the set S minus, that's 1. S minus V sub 1. And let's see here. Now we'll make this equal to capital S sub 1, right? So this is a new set. Now by corollary 2 earlier, the span does not shrink, right? So that means the span of S1 is equal to the span of S. Now, if S sub 1 is linearly independent, then we're done. Otherwise, we're going to go ahead and do another iteration of what we just did. So now we're going to take, now, if it isn't, then we're going to take a vector V2, right? That is a linear combination of the other members of S1, right? So take S1 and or take V sub 2 as a linear combination of the other vectors in S. Or S1 rather. The linear combination of the other vectors in S1, right? Now we're going to define S2 now. Well, okay, so it bears repeating. If S2, right, so now we're going to define S2. So let S2 be equal to S1 minus the set with the singleton set vector V2, right? Now, if S2 is linearly independent, then we're done again. But if S2 is not linearly independent, oh, hold on a second. One last thing. Okay, by corollary 2 again, remember, then the span, we also have the span of S2 equals the span of S1, right? Because again, by corollary 2, it doesn't shrink. The span doesn't shrink. Okay, so now what happens with S2? We're going to keep repeating the steps. If S2 is linearly independent, we're done. If it's not linearly independent, then we know that the span doesn't shrink, and the span of S2 is equal to span of S1. And then we're going to repeat this until a linearly independent set, you know, so we're going to repeat until we get a linearly independent set S sub j, right? We'll call it S sub j. Now, here's the thing. 1 must appear eventually, right? Because 1, we have a finite set. And 2, if we reduced this, if we kept going until we had the 0 vector, right? Then that itself would be linearly independent. So eventually we'll stop. Okay? So that proves well that's it. That's the proof, right? If S is linearly independent, we're done. Otherwise, we're going to find a vector V. There exists a vector V1 such that it's a linear combination of the other vectors. And then we're going to use the fact that define S1 as S minus that singleton set V1. And so since we can look at that, we know by corollary 2 that the span of these two sets is the same. Okay? Then we could take let's see here. And then what happens is we ask ourselves the same question. If S1 is linearly independent, then we're done. Otherwise, we're going to take another vector, V2, from S1, because there has to exist one that's a linear combination of the others, right? And if we then define a new set S2, where we take S1 minus the singleton V2, vector V2, and then of course, by corollary 2 again, we know that the span of S2 is going to be the same as the span of S1. And if S2 is linearly independent, then guess what? We're done. Otherwise, we just keep repeating the process until either we find a set that's linearly independent or we end up with the 0 vector, which is linearly independent anyway. And so we're done.